lalu nggak sempat.
That's alright, Pak. Terima kasih sudah datang juga.
Gimana kabarnya? Baik.
Baik, Pak. Baik. Pak Emir masih kayak dulu, nggak berubah, Pak?
Alhamdulillah.
Alhamdulillah, Pak.
Ada Pak Toga juga.
Yeah, I see that. Hello, Pak Toga. How are you?
Hi, Ira. I'm fine.
Good.
Still good shape, yeah.
Good. So, shall we start?
Yeah, okay. Then we will start now. Okay. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi semuanya. Good morning. Again, from here to Melbourne. I think it's about to lunchtime, right?
It's past lunchtime. It's 1:30 in Adelaide.
Okay. Jadi selamat datang semuanya. Sekali lagi selamat bergabung juga di acara kita Sustainable Architecture Weeks untuk yang kuliah kedua hari ini. Kita bersama Profesor Veronica Soebarto dari School of Architecture and Built Environment University of Adelaide. Kita meminta Prof Ira di sini yang sudah banyak sekali pengalamannya pastinya di bidang building science untuk mengisi beberapa kuliah, dan hari ini adalah kuliah yang kedua Prof Ira ya, di mana Prof Ira akan membicarakan tentang analisis building performance in relation to thermal comfort. Untuk informasi, Prof Ira, hari ini kita membuka kelasnya di kelas BIM atau Building Information Modeling. Itu adalah kelas untuk S2 sebenarnya, postgraduate. Jadi mungkin untuk yang hadir di sini, karena kami lagi-lagi membuka link ini untuk siapa saja sivitas akademika di Universitas Indonesia, khususnya di Departemen Arsitektur, bisa ikut. Nah, mungkin informasi juga untuk siapapun yang ikut di sini, karena levelnya sudah di kelas yang master, gitu. Mungkin Prof Ira hanya akan berbicara sedikit saja tentang basic what is thermal comfort, ya gitu. Kita upayakan tetap bisa menjaring semua pertanyaan di ujungnya nanti, tapi memang kelas ini dikhususkan untuk kelas Building Information Modeling, seperti itu. Okay, then Prof Ira, shall we start now?
Okay, thank you.
Thank you.
All right. Okay, selamat pagi semua. Good morning. Ova asked me to talk about analysis of building performance in relation to thermal comfort. Understand that this is a course in building information modeling, but as she said, because I understand there are other students who are attending who may not be in the same class, I thought it would be great to start by talking a bit about thermal comfort. Now, I might be spending a bit too much time on the thermal comfort because I think it would be quite important rather than on the building modeling itself, or maybe it's going to be half and half. Let's see how we go. And as last week, if you have any question, please just interrupt me and speak up. Please don't use chat because I'm not going to look at chat. And just speak up, or if you want to write a chat to Ova, and Ova can just then interrupt me and ask the questions. Okay? And feel free to turn on your camera so I can see who you are, and we can have a bit more conversation rather than a one-way lecture. Okay, so thermal comfort. What is thermal comfort? Now this time I'd like to ask if people could give me a very short answer for this question. So did the concept of thermal comfort exist in traditional architecture? Can anybody give an answer or give opinion on this? Anyone? Don't be shy. Bahasa Indonesia juga boleh. Apakah konsep thermal comfort ada di traditional architecture in Indonesia or anywhere? No answer?
Ada, Bu.
Ya, silakan.
Karena dengan menggunakan material lokal itu, yang notabene kalau di rumah tradisional itu kan dia pakai bambu atau kayu, di situ bisa mengalirkan udara sehingga bisa melepas panas dan menciptakan kenyamanan termal di dalamnya.
Okay, all right. Is that what you found in a study or research, or you're guessing?
Read a journal.
Okay, great. Okay, all right. Well, I'd like to share an experience, and Pak Toga, I think you can jump in here. I remember when you were trying to do some study or survey, I think it was it Sumba or somewhere
Flores.
Flores, exactly.
Yes, Flores.
I remember you mentioned that you were having troubles getting the answer from people. When you ask how they feel in their house, they feel nyaman or not, and they kind of said, ya apa itu ya, ya nyaman lah, ya sambil duduk-duduk ngerokok, and whatever the answer is, it's not about thermal, it's about they feeling comfortable, but not necessarily relating it to thermal. Is that right? Is that your experience?
Yes, yes.
Yeah. So despite the fact that we often read that people in the vernacular or people who did vernacular architecture understands that, but is that really the same understanding of thermal comfort that we understand now, or is it something else? For example, we know that in some traditional buildings, yes, they do build the building or traditional building with very light material to probably allow the air to go through. But very often what we see is the windows are very small. So, and then you go in there, and this was not my photo, but I remember last year I went to Flores and Sumba as well. And we went to some of the traditional houses, and inside the building actually is quite stuffy, sumpah. And we do wonder, or I did wonder, how did they cope when they felt hot? And often what they do, they just go outside. They be in the shade, they just sit among, plants and so on. So it's not that it is often the case that the building would provide comfort as we know it now, because there are other ways of them to feel comfortable. So the notion of thermal comfort that we know now, where a building has to provide this comfortable condition all the time, I don't think it's really the case. It may happen sometimes, but again, people don't necessarily live inside. They go outside. Some case, yes, they have windows, to have windows open, to have the air go through, but it's not always the case. And you see that in many, many traditional buildings, even in Indonesia. However, whoever answered before, I think you're right too. In some architecture, some traditional architecture, yes, they do know that bringing in fresh air is important, and they did in a way that it's done in a more a traditional way, but it works. So for example, using earth as the way to cool the building, so ground earth principle or ground cooling principle. In this case, this is in the Middle East, in Iran, they use something called kanat, which is bringing in hot air, going through the ground, which is cooler than the outdoor temperature, and therefore it brings in cool air, because then they have a wind tower to also let the hot air out. And sometimes you also have the principle of wind catcher. They bring in the hot air, and then they put something called like evaporative pad, like wet pad or wet mat. So then the air would go through this condensate and bring in cool air to the building. So yeah, some traditional building does that. But again, sometimes in the areas that it can get cool, they put lit fire. So then the fire brings warmth to the people, and it brings to comfort, so-called comfort to the people. So in a way, there are several ways for us to be comfortable. Either we move to another place, like the photo that I mentioned before. Either we regulate the rate of our internal heat generation. So if you feel cold, then you drink hot drink. Or if you feel warm, then you eat cold drinks. Or we increase or decrease activities to regulate the rate of the heat coming to the body, or regulate how much heat is lost to the outside, to the surrounding. So once again, we change clothing when we feel too hot. We take off our clothes, let our skin evaporates, the sweat, and then we feel cooler and so on. Or sometimes our body would contract, like when we feel cold, we become a bit tense. We increase the muscle tension to create this energy, the heat inside the building, inside the body. Or we regulate the thermal environment, so open, close doors, turning on fans, and that also happens in a new building. And this photo, this is my daughter when she was 8 years old. I found it interesting that yes, we open the windows to let the cool air in, And she probably was too busy reading a book. It was sunny inside, so she wore a hat inside the building. I thought it was pretty funny. Rather than moving the chair, she thought, oh, well, I just wear a hat, so I feel a bit better. However, the concept of thermal comfort as we use it now, which is, providing a thermally comfortable condition in a building for the people all the time, it really was a 20th century invention. It wasn't something that traditional buildings provide. It wasn't something that a traditional building would provide this comfort 24 hours a day, 7 days a week. Anybody can answer, when did the concept of thermal comfort, as we know, we use it now, started? When did the demand for thermal comfort really start? Anybody wants to answer that? Anybody knows? Can take a guess? Yes? Who's answering that? Oh, Pak Sadili. Selamat pagi, Pak. When did it start? When do you think it started? Okay, to save time, I'm not going to wait any longer. So this thermal comfort, as defined by ASHRAE, or the American Society of Heating, Refrigerating, Air Conditioning, also by ANSI standard, the national standard, it is basically understood as the condition of mind that expresses satisfaction with the thermal environment, and is often assessed by subjective evaluation. So subjective evaluation is, we said, oh, we're too hot or too cold or slightly cool or slightly warm. But it's a condition that we say we're satisfied with the thermal environment. Whereas in a traditional building, it's probably people not necessarily satisfied all the time, but they just go outside. They do something else to make them feel comfortable. So when did it actually start? It actually started by this guy back in 1902. So this is Willis Carrier. The notion of thermal comfort that we know now, that we said, okay, building has to provide a thermally comfortable condition for the occupants all the time, started off with the invention of air conditioning. And it really began with a printing company. So this is really interesting. It's a printing company in New York. They found that the humidity in the Brooklyn plant ruined the color register on the ink. So the ink, when applied to the paper, it misaligned. So it doesn't match with what they want to print because the humidity ruined the paper. So this guy, the head of these sales of this company, then because basically he was asked to fix the problem. So then he asked an engineer, Willis Carrier, to develop something to solve this humidity problem in the printing office. And then Willis basically recognized that climate comfort relates to the production requirement. And this is when he started developing air conditioning. So I'm not going to go through, of course, the big invention that he did, but basically it changed the world. Basically, it started off by affecting the printing company. So this image, they show that the printing got better once the factory got air conditioned. But that invention then started to spread very quickly. And this image, which came from this website, from a Carrier's website, say the air conditioning led directly to summer movie blockbusters as people came to cold theaters to escape the heat. So this is summer, but look at these people are wearing jackets and hats and coats because they're going to a refrigerating plant. It's like they're going to a refrigerator because it's so cold. And that's what people then demanded. So it says cooled by refrigeration. And since then, because we knew how to control the environment, we started demanding to be thermally comfortable inside the building, not just go outside. Don't just go outside. We need to be comfortable inside the building. So people demand to be thermally comfortable, and it has become a commodity. However, although you can tell that I've got a cynical view about this air conditioning invention, but Carrier developed something really, really important, something what we call now Psychometric Chart. So I'm not sure those of you who learn building physics were exposed to Psychometric Chart. Basically, it's a chart that shows the relationship or any things that relate to air. So it's a measure of what happened in the air, whether it's the dry bulb temperature, which is the temperature that we measure with thermometer, the amount of humidity or moisture in the air, which is sometimes expressed as the absolute humidity or relative humidity. And often this is what we say a lot. So relative humidity, you know, we hear in Indonesia, relative humidity is often between 70 to 100%. So 100% is, you know, very humid condition. And so the lines here are the relative humidity lines. This is the line of the temperature. And bear with me why I show this, because this is going to lead to the, later on we'll talk about building performance. So for example, what does it mean? So let's say this is the condition in, say, in Jakarta, sometimes reach 32 degrees in the middle of the day, and maybe that not that humid, 65%. And we want to bring it down to 24 degrees, because that's probably what we think, you know, it can be a bit more comfortable and not as humid. So just reduce it to 60 degrees. So this psychrometric chart basically explaining how the air conditioning system has to work. So first of all, it has to cool the air, so reducing the dry bulb temperature. See, this is called sensible cooling. And then it has to reduce the humidity, so along this humidity line. And then sometimes you may have to reheat it a little bit to bring it back to the 60%, because when the air is cool, it tends to be more humid. So if you want to make the air less humid, you dehumidify it. This is the dehumidifying process, and you bring it back to here. So basically the principle is often, particularly in the hot humid climate, what we will do is we dehumidify the air, and at the same time, we do the sensible cooling. So the sensible cooling go this way, horizontal, and then dehumidification go this way. Or sometimes it go this way. If you go this way, you increase the temperature, because going right is increasing the temperature, going left is decreasing the temperature. So just keep that in mind for a while and why I'm showing this. Okay. Now let's wind 30 years later. There's a guy named Gage or Gage who was interested in the relationship between human body and environment. And basically Gage or Gage said that to maintain the internal body temperature of 37 degrees, basically what we do is we need to have the heat coming to the to the body, and the heat can be from our activity. Or it could be from the food that we take. So we create energy in our body, but at the same time, we also lose the heat. So we can lose it through our respiratory system. So when we breathe out air, we basically lose some heat. We also can lose body heat through our skin, when we're sweating, through by evaporation, or simply if our body temperature is higher than the surrounding environment, then we lose the heat. But our body basically try to balance this, and we need to maintain this condition. So what happened is, so these two, basically, as I mentioned, is affected by food intake or activity, whereas these can be affected by our surrounding or our clothing. So when the surrounding us is warmer than our body would lose heat. But if we don't want to lose that heat, let's say if it's cooler, we are in a cool environment, we don't want to lose the body, the heat or of body, then we put a lot of clothing, right? So we reduce the heat loss. What this says basically is these are the factors that affect internal comfort. So our activity, our clothing, and then these four factors. So temperature, humidity, radiant temperature, and air movement. For example, again, if it's warmer surrounding our body or outside our body, we will have the heat coming into the to the body. And to make sure that we don't overheat our body, that's why then we release that heat through evaporation, through sweating, and so on. As a designer, this is what we can do. We can't really control what people do in a building. We can't really control what people wear. It's up to them. But as a designer, we can affect this through our design, or in the case of Carrier, he created air conditioning to control the temperature. Let's wind several years after, and I'm sure some of you are smiling looking at this photo. It's okay. Then this guy came along. He basically, his name is Fenger, or Paul Olof Fenger. He's a Danish scientist. And he was studying the relationship between the physical parameters of environment, as well as the psychological parameters of people, as well as perception and well-being. So what he did is he had 128 college students as participants, and he did study in a climatic chamber where he can control the environment. And what he did was he varied all those parameters. He varied people activity, clothing. He asked people to wear thick clothing to almost nothing at all. He varied the air temperature, humidity, radiant temperature, as well as the airspeed. And he basically asked people to answer questions such as, do you feel cold? Do you feel hot? Do you feel okay? And so on. And then he found out how to correlate all of these factors, which really this becomes the standard now that we use in thermal comfort standard. One thing that he found or he developed is something called PMV. PMV is predicted mean vote. Don't worry about the equation. I'm not gonna, I don't even do this myself because there is a program that can do it. But basically, what it says here is he found that people tend to prefer to be in this between slightly cool to slightly warm. So he asked question in this 5-point scale from hot to cold. And then this is what he called the neutral condition. And this is what he thinks, or the study found, that that's what people were after. So predicted mean vote is the prediction of where or how people are going to vote in this 5-point scale. And he found that between minus 0.5 actually to 1.5 is what people are after. The other thing that he developed is something called PPD, or percentage of people dissatisfied. So whilst PMV is saying how cool or how hot they are, this is expressing how many % of people satisfied in that condition. So as you can see here, this is the PMV vote on the bottom, and this is % of people dissatisfied. So as you can see, when people vote between minus 0.5, which is slightly cool to slightly warm, okay, the percentage of people dissatisfied with that condition is only 10%. In other words, 90% of people are satisfied. And the more you go further from the neutral condition, the more people feel dissatisfied. And he found that 80% of the population would be dissatisfied when they feel cool or warm. So that's pretty much what he found. Now, later on, that study then started to form what we call this thermal comfort standard, and it expressed, remember that psychometric chart, in the chart of the psychometric chart. So basically, these are the temperature or dry bulb temperature. This is the relative humidity. And over time, the standard actually changed. And then what they found basically is this is the condition that more or less we would feel comfortable. So between, let's say, 21 degrees to 27 degrees, but depending on the relative humidity. However, the study also found that when you increase the wind speed, so you put fan on or you have fan running in the building, we actually can expand our comfort. So then, even though it's 32 degrees, if there's fan running at 1.2 meter per second airspeed, we can still feel comfortable. Similarly, if we have a lot of sun coming to the building, this actually can extend to the left a little bit. Okay, so that's pretty much the principle of the classic or the conventional thermal comfort standard, which we still use until today. However, at the same time, there were other studies. So for example, Webb then looking at thermal comfort studies in the tropical climate and comparing it with studies in other countries. He looked at studies in the UK and found that thermal comfort in Singapore is quite different, or in India are quite different than thermal comfort in the UK. So this is the result that he found. So on the left here are studies in England or in the UK, okay? So English studies is right here. On the right-hand side here are studies in Roorkee or India, the plus signs, and in Singapore, or in Baghdad, sorry, in Baghdad, and this is Singapore. So these are all the hot climate, hot humid, and then in the cold climate. Have a look at the range of temperature. So in England, these are the range of temperature that people feel acceptable when they feel neutral, or between, you know, comfortably warm and comfortably cool. In the tropics and the hot climates, look at the range of temperature between 32, 37. And in Singapore, it's about 29 degrees. So is thermal comfort universal? I don't think so. So that study basically led to several more studies. Humphreys, for example, looking at what we call the adaptive feedback, that found that the outdoor temperature actually affects how we feel indoor. So when we expect it to be warmer, such as in the tropic or in the hot climate, then we actually can accept a warmer condition. Whereas people in this climate, which is cooler climate, or people in an air conditioning building, if they expect to be in a cooler climate, then they tend to accept condition that is in much lower temperature. So same, Elysium also found the same study, and our researcher, my colleague in Sydney, or at the time he was in Queensland, Richard De Deer, then he did more studies looking at all the data, which led to what we call the adaptive comfort. So what he found, or what they found, something like this. So if you look at the clear circles here, is basically, again, the condition that people found it to be neutral in non-free running buildings. Free running buildings is basically naturally ventilated building. And have a look at this. So this is the result in the naturally ventilated buildings, or building without air conditioning, that people accept the condition even when the outdoor is 10 degrees, they can accept temperature as low as 16 degrees. And when the outdoor is 34 degrees, they can accept condition up to 30 degrees. Whereas if you are in an air conditioning building, it stops here. The comfort stops at 24 degrees. Above that, people start to feel it's warmer, or it's warm. It's not acceptable. And it's really interesting when you compare that in terms of what they found comfortable indoor compared to the outdoor. So this is in air conditioning building. Whether it's hot outside or cool outside, the range of comfortable temperature inside the building is only between 22.5 to 25 degrees, very narrow. In the naturally ventilated building, we can tolerate from even, this is going down, even 20 degrees, but even less, 16 degrees to more than 27 degrees. So that really says that there's two different standards that we can apply in buildings. One, if you are in air conditioning building, which tend to reduce the range of acceptable temperature. And when you are not in air conditioning building, you actually can tolerate more. So in the context of what we call, well, lecture last week, although we talk about socially sustainable architecture, but in the context of sustainable architecture, I guess you know the answer, right? So if you're gonna look at how we can make the building comfortable, then don't close it off, because if you close it off, put air conditioning, then people would expect to be in that condition. And when you are in that condition, obviously what it means is you don't want to be too warm, and what it means, the building would use a lot more energy. So in the summary, that thermal comfort really can vary between people, population, groups, even older, younger, can be different. And it varies between people in air conditioning, not air conditioning building, but really needs to be understood and assessed before you design a building for those people. So how can our design provide thermal comfort, and how can we assess this? Now, this is going to get to the core of the lecture, and sorry to spend a lot of time before, but I think to give that context is very important. I'm going to start actually with the actual existing building first, and then we go back to the design and design process and using building performance modeling to do that. Just an example. So we just finishing the study looking at the thermal comfort of people over 65 years old in South Australia, where we go to the house, we do interview, we did a little bit of what we talked last week about looking at the social aspect of sustainable architecture, looking at their demographic and so on. But at the same time, we're also looking at the building design, heating, cooling device, and so on. But I guess what in the context of this lecture, it's relevant to show what we did. So we also asked people, we did the thermal comfort survey basically. So we developed our own data monitoring devices, and then people answer the questions about how they feel and so on using this tablet. So we created a tablet, the tablet communicated with the data loggers, so we know at what condition they answer the question. So we know the temperature, humidity, airspeed, and radiant temperature at the time. And then we ask question about what sort of clothing they are wearing, activity, what they feel, sensation, do they want to be cooler, warmer, and so on, and whether they're satisfied or not, whether the air conditioning is running, curtain open, and so on and so forth. And we also ask about their health well-being. So the benefit of doing the study is to really confirm what people experience. So as you can see here, the red line is the outdoor temperature, and we found in this particular house, the temperature inside the house in March, which is a bit warm, is, you know, within that comfort boundary that we looked at before. So with this also, then we can look at when they answered the question. So for example, this is really interesting. So this is the temperature at the time they answered the question. We also can see when they answered the question. And it's really interesting. We see that some people answering the question even at night. So some people probably don't sleep at night. Anyway, we can see the percentage of temperature when it reached certain temperature, and then their sensation. So this is just to give you an example of what you can do in terms of thermal comfort. From this, then we can start looking at what we call the adaptive conditions. So this is when they, this is the temperature and this is what they feel. As you can see, they feel more or less comfortable or between minus 0.5 to 1 to minus 2.5, excuse me, is between about 22 to 27 degrees. So the range is quite wide as well. And what we do is basically then we will look at the building design, and then we start looking at what factors of the building design actually affect their comfort. So to represent the data, then we can put that in the plot as we showed before, which is looking at the thermal comfort, and we can look at the range of condition when it is inside or outside the thermal comfort zone, or we can use the adaptive model again to see that. So that's just an example of one how we can assess. But what happened in the new design? What can we do in the new design? All right. So very briefly, as you all know, that a building is affected by many factors, right? The performance of the building, particularly in terms of its thermal performance, is affected by the location, where it is, the condition outside, the building envelope, what materials, what design you have or you create in the building, and it also is affected by people inside the building. In the context of hot climates, like in Indonesia, what happened is during hot day or when the outside condition or outside temperature is higher than inside, you know that the heat will come through the windows, come through the wall, come through probably radiation depending on the material of the wall. So the heat is absorbed and then radiates to the inside, come from the roof or the ceiling. And if the building is on still, you know, raised from the ground, and the outdoor temperature is higher than indoor, you also can get heat coming from the floor. Very rarely, usually because the floor tend to be on the ground, it's cooler than the outside air, but sometimes this could happen. And of course, there are also heat exchanges between rooms, and people create heat, lighting, equipment creates heat. So these are all the factors that we need to take care of if we need to modify the indoor condition to make it more acceptable to people. And then there's also something called infiltration, which is heat that goes through leakage or cracks around windows, around doors, and so on. So in summary, that's the kind of thing that we're going to have to deal with. So all of this heat that comes to the building, as well as the latent heat, which is heat with moisture, with humidity, it may increase the indoor condition beyond what we can tolerate. Okay, so we talked about the comfort range before. So all of this heat can increase the indoor temperature and humidity beyond what we can tolerate. So our job is then, how do we get rid of it? Because otherwise, either people feel too hot or sweating, or they would be forced to use the air conditioning. The problem is, as you know, when you use air conditioning, you use a lot of energy, and it also creates greenhouse gas emission. And for the occupants, it also costs them money because they have to run the energy or the heat cooling system. So just to remind you again, back to the psychometric chart, if this is the comfort zone that we looked at before, and I just plotted this, the monthly outdoor temperature, relative humidity in Jakarta. Okay, for 6 months. I just did it for 6 months. So what happened is we need to bring this back to the acceptable comfort here. Even though this can increase to what we said before, 32 degrees. So this can go up to 32 degrees, which is, let me just draw it here. So this can increase to here. Still, what happened here is we still need to bring that temperature down. And as you remember, this is what we call the cooling energy, because what we do is we need to dehumidify and cool the air. And that basically can create a lot of energy. Let me just delete that one. Okay. Okay. How much heat needs to be removed? Well, let's just assume, say outside temperature is 32 degrees, and we want to bring it down to 28 degrees. Okay, assuming that's what we want to achieve. And to bring it down to 28 degrees really depends on the area of our envelope, our building, whether it's the window, walls, roof, and so on. And also depends on the heat transfer per unit area of the envelope. So how much heat can this material bring to the building? Okay. Because when you look at, and I'm not sure if all of you have done this, so basically how much heat will be gained from outside to inside really depends on the area, and the U value is called conductance, and depends on the temperature difference between outside and inside. So if the outside is much higher, of course, you know, there's a lot more heat coming to the building. If the outside temperature is the same as inside, there's no heat transfer because heat only move from the higher temperature to lower temperature. So I think that's pretty clear, right? So basically all the heat that comes to the building really depends on the area of our building and the conductance factor and the temperature difference. For glass, it also, or windows, it's not just the heat that is being conducted, but also the transmittance or the transmissivity that the heat goes through the glass. So you also need to know the shading coefficient or solar heat gain coefficient of the glass. So this is in ratio. And then how much heat is outside, how many percentage the heat can come into the building, and the area of the glass that would determine how much heat go into the building. And also once the heat goes to the building, it also radiates out, or the air also is circulated by convection. All of these need to be taken care of, okay? So basically what happened here is, oh, sorry, before that, then as I mentioned before, there's also heat coming through opening like this, or cracks, people, lighting equipment. So what happened here is how much heat needs to be taken care of, whether it's by opening windows or through air conditioning. It really depends on the total heat that comes from the building envelope, infiltration, ventilation, people, lights, and equipment. All of these becomes what we call cooling load. So this, if you are using air conditioning, this determines the size of your air conditioning system. So the size of the air conditioning system really depends on how much heat that needs to be removed. And how much heat that needs to be removed depends on the building materials, the design, the openings, people, lights, equipment. This cooling load, if you look at it over time, then becomes what we call energy. Okay, so for every hour, and you multiply it by 8,760 hours a year, you got the total cooling energy, and how much, total cooling load, and how much energy is needed depends on the efficiency of the cooling system. So if you divide the cooling load by the efficiency of the cooling system, you got the cooling energy. And if you're concerned about the environment, this cooling energy can also be transferred or translated into greenhouse gas emission by knowing the greenhouse gas emission equivalent for 1 kilowatt hours of electricity. And if you're interested in the cost, basically, once you know the cooling energy, you can multiply by the electricity cost, and you know how much money your client will spend for making the building cool. So the point that I want to make here is, particularly these 4 aspects, these are what we as designer can control. We design the building, we determine the area, the size, the dimensions, we determine the materials, we determine whether there are cracks or not through our detailing of all the building construction. The way we open windows will determine how much heat coming from ventilation, and we also determine how much lighting will be needed in the building. If you design a building that doesn't have many windows or openings, then even during the day, people will turn on the lights. And when you turn on the light, you bring in heat from the lights, it increases your air conditioning load. So building design play a big role under this. So what does this have to do with thermal comfort? Well, if you remember that equation that I showed you before in terms of how much heat comes to the building, you know, this depends on the area and the materials that you use. But have a look at the one on the right here. This indoor temperature is what we take as what we call the condition that the occupants consider as thermally comfortable. So if occupants can accept higher temperature, 27 degrees, the temperature difference between outside and indoor is less, and therefore the heat gain is less, therefore your cooling energy is less, therefore the building would use less energy, pay less money. But if we expect this to be really low, because people like to be freezing in the building, then obviously the temperature difference is higher, your energy needed to cool the building becomes higher. So the understanding of thermal comfort does affect how much energy a building will need. Of course, we're not going to be able to force people to, you know, increase or widen the range of temperature that they can tolerate. But if we design a building in such a way that people have more connection with outside, that they don't expect to be in this ice box all the time. So remember we talked about last week about social sustainable architecture or social aspect of sustainable architecture. One of the aspects is about well-being, about relationship with outdoor. So if you can design a building in a way that people can have better correlation with outdoor, I think it will affect how much energy is needed to cool the building, because the expectation is different than if you put people in an icebox building. So having said that, back to the main core of this lecture. How do we then assess our building design so it will provide thermal comfort to the occupants? Well, you can do what I showed you before in terms of doing the calculation. You can do it by hand, but of course it takes a lot of times. Because if you think about the whole year, there's 8,760 hours, which means you have to do this calculation 8,000 more times. But also doing hand calculations is very hard to take into account the thermal histories. You know, the heat will be absorbed, radiated out, convecting, or being convected around the rooms and so on. So what we, well, many years ago, I think more than 60 years ago now, a lot of scientists found, or some scientists found, that you could do it through what we call building performance simulation. So what is building performance simulation? It's basically a computerized tool, which by using numerical methods, it can find solution to a realistic model of the complexity in the real world. So you simulate a building, you put it in a real location, and then you put it in the real time frame, and then using the basic methods or basic calculations, some of them I showed you before with this steady state calculation, but of course, in the complex building performance simulation, it's more complex than what I showed you, but hopefully you got the gist of it, you got the basic principle of it. So by doing this calculation, then the building simulation can predict the impact of outdoor, the impact of external shading, maybe ground surfaces, the impact of building envelope data, the impact of people, lights, equipment, and so on. And also, if you do use heating and cooling, or sorry, cooling system, then it can also predict the energy use. So with building simulation, what you can do is you can look at the solar access, solar radiation. You can predict the indoor comfort because the simulation can calculate with this all the heat exchanges that happen around the building or on the building envelope. What would be the temperature inside the building? What would be the humidity? What would be the airflow? Or it also can calculate the PMV that I showed you before. It could calculate the percentage of hours when people feeling comfortable or not comfortable without air conditioning. Or if you want to have air conditioning, it will calculate how much load. Remember, we talked about heat gain is the same as cooling load. Then it can calculate the energy consumption. It can calculate the cost and calculate the size of equipment. And then other things such as daylighting, maybe water usage, maybe solar water, and also embodied energy or materials, which is, I think, outside the context of this lecture, basically energy that is used to make the building. And maybe if you're interested in looking at creating energy or electricity from photovoltaic cells, simulation can also do it. Before I show you the simulation itself, so basically the simulation can be used in two things, in two modes. One is in a building without air conditioning, or when you turn off the air conditioning, you really want to see how comfortable the building is without air conditioning. Because if you turn on the air conditioning, of course, it would be comfortable because you set it to the temperature that you want. But the beauty of the simulation, you can do it for the what we call free running, because then it can predict various indoor comfort parameters. Or if you want to test how much energy is needed when you use cooling, then you set it so that you close all the windows and you said, okay, now I'm turning on the air conditioning. It will calculate the energy for you. So the process of simulation, if you haven't done it, basically, once you got the program, you enter all the input. What are the inputs? The inputs are what I showed you before. So let me just go back quickly. So the input for building simulation are basically this. You need to put the weather data or the location, which then pull the weather data file. So it's hourly weather data file. You draw the building like in CAD programs, and then it will get all the areas, all the dimensions. You enter all the materials of the building. You also put in whether there are trees outside, surrounding buildings, and so on. And then you put in how many people in the building, whether they use lights, appliances, when they use it, when there are no people in the building, and so on. And also if you have heating and cooling system. I think for architecture students, I always say to my students, always try to turn off the air conditioning to see how good the design is. I think this is what I always tell my students, but then if they want to test just to look at the energy, they can do it. So basically what you do is you put all the parameters. Then once you have all the input parameters, it's just a matter of clicking the button, execute the simulation, and you got the result, whatever result you want to examine. And then obviously you're gonna say, oh, is it comfortable? Nah, it's not. So how do you change it? Well, let's say if the building is too hot, then you said, oh, let's see what happens if I change the orientation. So you just click and change the orientation. Or you said, oh, I'm gonna add more shading. I put more eaves or overhangs. So you just redraw the building, extend it, and see the impact of that. or you can change the building materials, or you can reduce the window size, or make it wider, bigger, and so on. So there are so many building simulation programs. So if you want to know how many and what they are, this is the database for all simulation programs in the world. So you can go to this and go through all the programs that you want to use. I personally use, or we teach here several programs. So we teach a program called Design Builder, which runs Energy Plus simulation engine. We teach IES, which is an integrated environmental solution. That's a UK-based program. And lately, we've been using Rhino Grasshopper, and we use Ladybug and Honeybee as a simulation engine. So that's one way of doing that. But there's many other programs that you might want to have a look. And these are some of the examples that we did. So in this case, this is a simulation of an existing building. In this case, we're not looking at thermal comfort, but I just want to show you. So this is an existing building in Adelaide. That's the model. So as you can see, you model the surrounding buildings, and then you enter all the parameters of this building to reflect what actually happened in the building. And then there's another building here, which is, oh, sorry, that building is somewhere here. Oh, sorry, here, sorry, the white, in the white. And then the third one is this building that we simulated. And then what we did in this simulation is looking at the impact of urban heat in terms of its energy use. So what happened if the actual temperature increase, due to global warming, or there's a period of heat wave, how much greenhouse gas emission from the building would increase. So that's one way of doing simulation. This one is done by my students. So in this case, it's actually a design competition. So this is the existing building, the student model it, and they want to see the impact of having this ventilation here, for example. So they model the building. This is using Design Builder. And as you can see on the lower right-hand side, it then demonstrate or simulate or calculate the temperature inside the building at certain time of the day. And of course, then you can run it for the whole year or only a few days and so on. And then you can start saying, okay, is it really worth having this strategy? This one is, again, from some of our architecture students. So in this case, this is their design project. So then part of the design project, then they have to demonstrate that the building meets the comfort criteria. In this case, they use the program called IES. As you can see, then you can look at, shading impact and how much heat is received on the surfaces. And then what they did is looking at once again, the indoor temperature versus outdoor. So as you can see, this is in the colder, this is actually in the warmer period. As you can see, the temperature is very, very high when the building is just using normal glazing. And what the student did is started looking at other strategies. So when you incorporate opening windows, changing the window glass, and so on, and the temperatures start to reduce. So this is like the original or the initial design, and you can see the temperature drop here. And then this particular student also look at the impact of double skin facade. So looking at daylight into the building, once again, looking at the difference it makes by having this double skin facade in terms of indoor temperature. So this is the initial indoor temperature, the blue line. And then once he applied the double skin facade, the temperature dropped quite significantly. And then he started looking at, okay, what happened if the air conditioning is turned on, which means the windows are all shut. But it also showed that the cooling energy dropped quite significantly, more than half by having this double skin facade. These are another projects again. So looking at this mixed use building, and this student is really interested to see, or was interested to see, the impact of different kind of shading outside the window. So, so first, of course, like your design, you're looking at more basic principles, how we did it, and then he started doing simulation. So in this case, he wanted to compare if there is no shading on the outside, and you can see the temperature in the summer is quite high compared to the outside temperature. This is the outside temperature, so the inside is much, much warmer with the air conditioning. And then he start looking at when he applied this shading, then as you can see, the temperature started to drop. It's still quite warm here during the hot day. But then he also see, okay, what happened if these openings are actually, or these windows are actually openable. And you can see then once you open the window, the temperature drop quite significantly because you bring in fresh air. What it means here, then the building is not going to use too much energy because you let people opening a window, it brings the temperature down, people feel more comfortable. And if you do need to run the air conditioning, it's only during this period. Okay, so you can see that, then they can say, okay, I will only turn on the air conditioning between 12 to 4 o'clock just to bring the temperature down. But apart from that, you can just let the floor temperature. Another tool that you can use, then this is online. So if I click on this, it actually goes to the website of the Center for Built Environment. And you can use this tool online. So if you haven't tried it, come here, and then you can basically, you can enter in the temperature in the space, and you can see that red line or red dot moved. So when the temperature is higher, and this is using the PMV method, okay, the heat balance method, you can see, and then also if you increase the humidity, you can see, okay, that's probably not very comfortable. It says here, do not comply. But if you are interested in the non-air conditioning building, so same thing, you can use that tool. And instead of using the PMV, you use the adaptive method. Now you can also see, if you go to 27, as you can see here, now people are still okay with that temperature. If the outdoor, even if the outdoor is higher, and you said, okay, maybe at the maximum I can achieve, you know, if I can make the building to have 30 degrees maximum, then the building is good enough. So what do you do if it doesn't? Well, you go back to the design and you make improvement. What you can do though, also in this tool, you can also upload a file that has the hourly temperature. So instead of using just one point, you actually can grab the result from the simulation and then dump it to here, and it will give you all the dots of when the indoor temperature, and you can assess whether the building is comfortable or not. Okay, so in the last 3 minutes, in the summary, as you can tell now, building performance depend on the building design, the envelope, the materials, the dimension, orientation, shading, and so on. And it's also depending on the expected indoor conditions or the thermal comfort limits that we talked about before. And it influenced by the outdoor condition. Also, it is influenced by people activities, because we, as the occupants of buildings, would generate heat. Our activities would generate heat. It affects the comfort. So to assess your building design, I would suggest you use the building simulation, because then you can understand the impact of the surrounding environment and building envelope on the indoor environment. As you can see, you can test different strategies on the building, and you look at the comfort inside the building. You can also, so in a way, you can look at the indoor temperature, humidity, thermal comfort, percent of comfortable hours or non-comfortable hours. But again, if the building does need air conditioning, you can predict how much energy the building will need. And so to minimize it, obviously, then you can go back to the design, you can do other things to minimize that heat gain, therefore reducing energy in the building. And the process, once you got the model, it's very quick. Okay, you can run hundreds and hundreds of simulations. It should not be too hard. However, just remember, when you use building simulation, simulation can never replace reality. There's always assumptions that you make, because a lot of building simulation can't do everything. Also relies on the accuracy of the program itself, and also your skills in using the simulation. So you need to be well trained, because it's very easy to make a mistake, because it's just putting numbers, right? If you just want to look good, you can just you know, let's just say you use building materials that conduct very little heat. Whether or not that material exists, you know, you can make it up basically. But if it doesn't exist, then what's the point? So really just be careful when you simulation, because if you put garbage in, you get garbage out. What it means, if you put the wrong input, you get the wrong output. So if you are using simulation for real project, I also suggest that you have another person to look at your simulation model to make sure you don't make silly mistakes. My suggestion is we need to incorporate this assessing building design during the design process, so it's not going to be too late. Because if you don't pay attention to maintaining acceptable condition into the building, there could be two risk or two impacts. One, on the left here, there's a study that found when people are exposed to condition that is either too hot or too cold, the risk of mortality and morbidity are getting more. So people can, you know, die at very hot temperature. It's quite different. This is in study in Spain. This is in Bangkok, which is probably similar to Jakarta. The rate of death is not increasing as significant as, let's say, in Madrid, but still, as you can see, when the temperature increases, there's a chance of people, the death number of deaths increasing is even more. And the second one, of course, if your building is too hot, then the likelihood of people using air conditioning is more. And what happened is we just keep increasing our greenhouse gas emission. And I believe we don't want that to happen. So that's it from me. If there's any question, I'll be happy to answer.
Okay,
I don't know
thanks
if
so
that's
much.
what you expected, Ova, but maybe I just went too far on the thermal comfort bit, but I think it's important to give the basic understanding before we go to the actual simulation.
Yeah, oh, it's very perfect, Prof. Ira. Actually, what we have here from your study, we have a lot of experience from various places, yeah? And the definition about the thermal comfort itself is really depend on the self, right? Even though we are calculating the performance of the building, but still the users are the key. And thermally comfortable, that's the definition of different people, different situations, different locations. Yeah, I think you raised a very important questions about the thermal comfort. Is it universal? So I think everybody should be able to have the right answer now. Okay, Prof. Ira, do you want to have like some questions from the audience?
Sure,
Okay?
sure, definitely.
Okay.
Yeah, no problem.
Then I would like to invite questions or comments maybe from all of our audience. We have like 48 now. Kalau ada pertanyaan atau komentar, silakan disampaikan dalam forum ini. Langsung saja. Adakah?
Bahasa Indonesia juga nggak apa-apa.
Bahasa Indonesia saja. Silakan. Sambil menunggu, mungkin yang ada bertanya, Prof. Ira, sebenarnya kan kelas ini dari kelas BIM itu sendiri, ya. Kita mendatangkan trainer BIM certified dari Autodesk. Ada Kak Greg di sini. Halo Kak Greg.
Halo, halo.
Ya, mungkin bisa kenalan sedikit Kak Greg sama Prof. Ira.
Ya, oke, Prof. Ira, thank you very much for guest lecture here. It's very enlightening here. So, actually, I want to talk about our class. So, the class now we study about building information modeling, particularly using design authoring software of Autodesk Revit.
Yeah.
Especially for the purpose of building simulation, of course.
Good.
Yeah, so it's kind of, well, it's just starting now in this class. So maybe I can share some sample of thing that we do. Well, this is the one of exercise that students did. Basically, in BIM software, we can just put many of information such as any that you talked before, like the sun position, location, and also the function of the building that determines the people, activity, heat gain, and so on, and
Right.
also the material.
Yeah.
Actually, I have a question myself for you, actually,
Yeah.
that you already tried many simulation softwares.
Mm-hmm.
I'm interested in interoperability between the software and especially from those simulation software and the BIM design authoring software like Revit. And how is the workflow
Yeah.
if we
Yeah.
do it?
Very good question. And I have to say that is the problem that is still going on since I started doing simulation back in the 90s. The issue is BIM is supposed to be the link, the core of this, right?
Yes, yes.
And I think in Revit, you could also use, there is Revit, what's it called?
Actually, I usually use the internal engine of the thermal analysis, the thermal load analysis, and also the Insight 360.
That's
here.
right. Yeah, yeah.
Yeah.
So if you are within, let's say if you Revit, if you just use that, I think it's great because then you don't really have to go out of Revit. The issue often is in practice, a lot of detailed environmental simulation is done by specialized companies, and they don't use that program.
Yes,
and also
exactly.
because Revit is intended not to be the environmental simulation. So although it can do environmental simulation, it has limitation. So as a result, then people then use Revit to model the building and then transfer the model into, say, Design Builder or into IES. So they then create the IMF file or GBXML file, and then it would be read by another program. The problem is when you think about thermal simulation, let's just say thermal simulation. With thermal simulation, it actually almost doesn't matter. Let's say if you got a window, and I'm just using, let me just see. Let me just use a piece of paper like this, okay? So if you have a window that is here on this side, oh, sorry, probably not. Let me just,
Maybe you can check
maybe I
the
just
one that
annotate.
is not white, Prof. Ira.
Yeah, maybe.
The paper shouldn't be.
Let me just see. Okay. Oh, there you go.
Okay.
So you have a window here, which is in the BIM model. Of course, you have to draw the window as where it is, right? That's the window here.
Yes.
That's the window here. In the thermal simulation, what matters, as long as the shading condition is the same, it just needs the area, right? So whether your window is here and here, or just make one big window, it will give you the same answer. So what happened here, in the simulation program, often you don't need as much detail as you would have done in the Revit model. Also, for example, in the Revit model, because it's modeling the real construction of the building. So let's say you got a wall construction. You have to model the frames. Maybe you got, let's say you model the concrete column, you model the bricks, you model the window frames, door frames, and so on.
Yep.
It's detailed, right? But then when it comes to the simulation, the translation from the BIM model to the simulation often means that this frame, let's say we take a window frame, the window frame becomes not a window frame, it becomes like a square box with air inside. And then the simulation might think it's actually a room or a space and start calculating the heat transfer inside that, which is, it's actually not the case. It's actually just a solid material. And there's so many other things. Let's say if you have double brick walls, so you got a brick, air, and brick. When the translation happens between the BIM model to the simulation model, it depends on how the translation is done. The simulation model sometimes translate this air gap between the brick and another brick as a room, and then start doing simulation start doing heat calculation inside the room, and as a result it just takes forever. So the issue is interoperability is always an issue, because, and also now it's also a commercial issue. So Revit has their own. If then design builder or IS does another thing, they said, oh well, this is how we do it, this is how my company does it, I don't want to talk to you, because if everything is so easy, then nobody will buy my product anymore. I don't want to do it. So it is frustrating. It's really frustrating. So my suggestion is, particularly for students who are learning, probably for now, what matters most is the understanding that the students can get from using whatever it is. It could be Revit, it could be different tool, whatever. I think it makes, the issue of interoperability, I think, becomes a real issue once you work in practice, because you have to work with different consultants and different projects and so on. Then it becomes a problem. But
Yes,
once
agree.
I think for people who are learning, I think what matters more to me is what you get out of the tool rather than the tool itself. The tool is just a tool. I think that's what I'm going to say. So, but look, we did survey on this. We tried to come up with solutions, and every time somebody tried to come up with a solution, another company would pop up and said, no, do it our way. And also in practice, it's really interesting when you talk to a lot of, I don't know about Indonesia, but here in Australia, when you talk to a lot of consultants, so the architecture firm gives them the B model, expecting that they use the B model to do the simulation. And the consultant will look at it and say, too much detail in it, I don't want to use it. I do it. So then they would rebuild the same building in another software to make the simulation faster. And it sort of defeats the purpose of having BIM, but that's reality. I talked to a company who did the simulation for the London Olympics, so some of the stadiums there. Again, they use Revit, they use the model, but when it comes to simulation, this is a big company. They chuck it out and they just redid everything with IES because they think it's too hard. So there has been some PhD research trying to solve this interoperability problem, but when the companies don't want to take it on board, it's really hard. So I don't have the answer, but you raise a very good question. That is a problem.
Yeah.
Yeah, but it's good that you. So if you, I think my message to the students is, stick with Revit. It's a good skill to have because companies now, of course, most companies use Revit. And if you can make sense of the simulation that comes off Revit, I think that's fine, as long as it makes sense. And then once you start working, if the company that you work for doesn't use Revit environmental simulation and you use another program, you just have to learn the other program. It's just a tool, I guess. But that's great to see that.
Yes.
Yeah.
Have you tried to compare the result between the one resulted in Revit and also in IS?
I have to say I have never compared Revit with IS. I did compare IS and Design Builder, and in the past, also we got a program in Australia called Accurate. If you model the building correctly, they tend to give the same answer.
Right.
So, if you model the building in the same way, the materials is put in the right order and so on. If you do it very carefully, it tends to give the same answer. I mean, it's probably differ between 5 to 10%. The problem is some software doesn't have the same feature. So for example, some software would say, oh, when you model a window, just include everything, the frame and the glass area, make it one area. Some programs said, no, you have to separate it. You have to create the window, you have to create a window frame, and then you have to model it. So for example, if you use Design Builder and if you use the capability of the window program, which is related to Energy Plus, and you have to model the frames, the glass separately, it may give you different answer. So it really depends on how you model it. I mean, sometimes even, as you probably know, Greg, if two people using the same program, simulating the same building, the result could also be different depending on how you model it.
Yes, yes.
So it's very tricky. So that's why I said,
Yes.
if you are working in a real project, it's very important to have not just one person, but at least another person to compare, to make sure he did the right thing or she did the right thing. Because especially when you have to enter, say, infiltration rate, very easy, you mistype a number, right? You want to put 7 and you put 70. And all of a sudden the result will be different. But if nobody is checking it, nobody knows. And then the building will get built. And then once it's built, people say, hi, why is it not performing? It's different than the simulation. Well, it's probably because the simulation was wrong. So yeah, it is, I would say, I love simulation. It's a powerful tool. It's a really powerful tool. You know, you can predict something before you build the building, so you can save a lot of money. But it also is kind of, there's a danger, there's a risk in using simulation if you don't do it properly. And you would read a lot of studies that show the simulation results, or the reality is so different than what is being predicted. And again, once the building is built, the other factor, as we talked about last week, are people, right? People use the building different from what the assumption in the simulation, the result would be different. So there's so many factors, but yeah, it's good to know. It's good to know that the tool exists. And I think if you're aware of the problems with simulation, when you work, you will not get manipulated by other people. Because, you know, very easy, people would say, oh, I have this green building and, you know, it has so many stars and it is predicted to use so much energy, whatever. But as you know now that it can, I mean, it's so easy to manipulate the number. So as long as students are aware that there are issues as well as benefits of using simulation, I think that's more important, you know, so that you don't get lied on. You don't, you know, people don't lie to you because you can check it yourself. So I think it's good that students know how to use it. Sorry for the long answer.
Actually, I have one more question. Can I?
Sure. Yeah.
Okay.
How about for the green building rating? Is there any specific requirement of the result? I mean, like specific method that you have to do this way, you have to do this way?
It depends on the country. I don't know in Indonesia. In Australia, there is a protocol, what program you can use. So it has to be so part of the Green Star rating, for example, about 60%, I think, of the assessment is based on energy performance. So energy performance in that case means you have to simulate the building beforehand. And the simulation programs that can be used in Australia for particularly big buildings, there's only, I suppose, 2, Design Builder and IS. Those are the tools that people use. If there is a new tool, it has to go through like a testing process. So then you have to compare the result from that simulation with the results of the acceptable tool. And it has to meet some protocols. And then if it doesn't meet the protocol, you can't use it. But I'm not sure in Indonesia whether you have the protocol or not. Do you know?
I think we still don't have exact tools for the submission requirement here. So we also try to talk with Green Building Council Indonesia and what kind of the result that is accepted for the submission, like that.
Yeah. So I'm sure Green Building Council International has some standards. So if Indonesia is part of that, I think they should at least follow the same protocol or similar protocol. In the world, around the world, I think there's only, I mean, although there's so many programs, the ones that are usually used and people think it's acceptable and reliable, sorry, the results are reliable, are Energy Plus,
Yes.
which then Energy Plus is the simulation engine, and the front end, the user interface is, it could be Design Builder, it could be, oh, there's another one. It's using, it uses SketchUp.
Open Studio, Prof.
Open Studio, yes, correct. Yeah, Open Studio, but the simulation engine is Energy Plus. And then another program is, as I said, IES. Although people who work with Energy Plus always has problems with IES, they don't really believe the result, but anyway, that's okay. And the third one is, there's another program which is a bit more research-based, but it's also reliable in terms of the result. And that is a program from Strathclyde in Scotland, which is called, the name just escaped me. It's 3 letters. Now, I'm not 100% sure with Revit. What is the simulation engine behind Revit?
The simulation inside the Inside 360, the engine is Energy Plus.
Oh, okay. So if it's Energy Plus, then I think that should be acceptable. That's my understanding.
But the interface and the result, I think, I'm not sure, is it acceptable? I mean, the result sheets from the Inside 360. I mean, the format.
Ah, okay, the format. I guess that depends on what the green sheet is doing. So in Australia, for example, the energy part, what they require is the breakdown of the gas and electricity use, and then the greenhouse gas emission. So, and then within that, of course, there's protocol about simulating cooling energy and so on. And then within that, there are protocols about the user profiles, use patterns, you know, that sort of thing. So there's a protocol on that. In terms of the result, I think they just require the normal output of that program. So I'm not sure. Yeah, again, I can't give you the answer on that. It really depends on what the country wants to say. Yeah, yeah. There's a question from Tria.
Yes.
So I was wondering if you have a project or example of building that had a performance simulation to design and build it based on those simulation. Do you find any error miscalculate any difference between reality, or it just looks fine? That's a very good question. So I happen to know the architect of, there's a building in Manchester. Hang on, what is the name? It's their city hall. And they did use simulation, they use IES. And they built it according to that. Also, as I mentioned before, the London Olympics, some of the stadiums, they simulated the airflow to make sure, I think it was the swimming Olympics, a swimming stadium. They wanted to make sure that people, the people in the podium would feel comfortable and so on. So they used that and they built it according to that. My understanding is that the results were quite close to, excuse me, the performance in reality were quite close with the simulation. However, having said that, there are many other examples that show the results are very far, or the actual performance very far from the simulation. I know some buildings here in Australia that had that problem. There was a study, I don't know if you're interested to look at the report. There was a study done by one of my colleagues looking at something like 60 buildings in Australia, office buildings and hotels, and comparing between simulation and actual performance. And I think 30% of those buildings, so 20 buildings, performed quite differently. Some were much better than predicted, some were much worse. So, and then often the reasons, there's so many reasons. One could be the way the building is built. So even though, you know, it uses the, I can tell you another example. So this is a housing complex. So it was simulated and built, supposed to follow what is being simulated, what was simulated. In reality, excuse me, in reality, the builder did not put as much insulation in the roof as in the drawing. So the building leaked more heat and used more energy for heating, for example. So often is the way it is being built. Two, when it comes to the heating cooling system, often the actual equipment that they install, the control was not as planned or not as simulated. So the equipment itself can use more energy than what they thought it would because of the way the control is done. But the third issue could be the occupants. So I'm not trying to blame the occupants. Often what happens is when you simulate a building, you make assumption about how people will use the building. And this back to my lecture last week. But if you never ask the owner how the building will be used, and if you never spend time with the potential occupants about how they're going to use the building, and then you just use standard and you just assume this is how people are going to use the building, you can get it wrong, because once people move in, they probably never use the building the way you simulate it. So it's really important you got the occupancy behavior simulated correctly. So currently, one of my PhD students is looking at how people in Darwin, in the tropical climate in Australia, live, because our building rating system for housing have assumption that people will be in the building from this time to this time, that they will turn on the air conditioning between this time and whatever. And my student just went to Darwin, did survey of 40 houses and found that that's not how people in Darwin live. They don't turn on the air conditioning at that time. They mostly open the windows. They have different ways of using the building. So you can imagine if you simulate the building with the wrong assumptions, the result would be very, very different. So, Tria, is that answering your question or you have other questions?
Yeah, actually, that's the thing that I want to ask you, because I actually study at RMIT in Melbourne, and I know that all my lectures also like saying all the simulation needs to be understand. It's just a tools that you have to understand that sometimes tools make errors. So yeah, that's why I haven't seen any real buildings that use that simulation and see it and how it looks like, and how the like how people live throughout the year, especially in Australia. They have summer and winter is so extreme. So maybe you can share more those things.
Yeah. Look, if we have time, let me just show you very quickly. This is a building that we monitored, and my friend happened to be the one who, let me see, did the simulation. So it wasn't her fault. And the building was, the building was designed, and then she did the rating and simulated the building. And the building in Australia is something called 7.5 star. Basically, it's, let me just share my screen. So that's the building. So So that's the floor plan of the building, and north is that way. So she simulated the building as it was going to be designed. So with, materials and so on and so forth. And it was supposed to achieve what we call 7.5 stars. So it uses some energy for heating and cooling, but, not too bad. And that's how they were supposed to be built. And in that simulation program, there is an assumption that when the temperature inside reaches certain point, or when the outdoor temperature reaches a certain point, the window will be open. And so people would feel more comfortable, and they only need to use cooling at the very hot temperature. Now, look at how the building is built. That's how much you can open the window. So
that's so small. Like super, super small.
Super small. So what happened? So we monitored the house and we talked to the people, and they basically said, when it's so hot, and this is a low income housing. So some people said, well, when it's too hot and I don't want to pay for the electricity, I just go to shopping mall. I just stay in the mall until night and then go home because I can't open the window. So I'm not sure whether the simulation was wrong, meaning that they did not check with the architect how much that the window can be open, or when it's built, they put the wrong window. I'm not sure. I was told also that there is in the code, in the building code, when you live upstairs, the windows should not be open more than 10 centimeter because people might jump out. Duh. But this is not even 10 centimeter, that's 5 centimeter. That's it. And there is no other windows. There is no other openable windows. So yes, the building was built according to what was planned, except the way the window is designed or built is not according to what the simulation was done, or vice versa. Or the simulation didn't know that the window can't be open that much. So then it looked like it was good. And then we monitored the house. Oh, let me just, sorry, I just continue to share the screen. So, and then we record the temperature in the building. And let me see, oops, what's going on? Let me just see. Oh, okay. So, all right. So that is the, I mean, it is hot outside. The gray line is the outside condition, and this is the inside. But look at on the right-hand side. So the inside gets up to 37 degrees because it's hot outside and they can't open the window. So it's pretty hot inside. Yet this was not captured in the simulation. The simulation thought the building would be cooler than this. So yes, it happened. So did you go to the architecture school, Tria, or the building property?
So I went to Master of Design, Innovation, and Technology. It's on School of Design at RMIT.
Oh, okay,
So,
right,
yeah,
fantastic.
and I took one of sustainable class. So I cross studies to environment
building.
and yeah. And
okay, so who was teaching you? Was it?
My God,
Myla?
I forgot this. Trevor? Sorry, I forget the
Trevor?
name. Trevor. I
okay.
guess this is the one. He's still like young, like the cycling. I barely remember him, but yeah, he just told what you just told about the green buildings and stuff. But yeah, but it was nice to see you.
Great. Okay, Tika, I just want to ask initially a bit and ask you that we tend to use content into space, but say we just hit. Yep, good. Do you think Light 12 was worth trying for those who live in the tropical country? Okay, Tria, what do you think before I answer your question? Oh, Tika, sorry, Tika. So, so the question was, do you think light well worth trying? Because when you use daylight, it also produces heat. Okay, well, my answer is, if you use daylight properly, it should not create too much heat, because the technical term for daylight is basically sunlight without heat. So daylight basically, if you really use the word daylight, daylight actually means the indirect or diffuse sunlight. So you could have a window, but if you have overhangs and it blocks the direct sunlight, you will get daylight. And there's not much heat coming from that. It's just the same air temperature. So the temperature of the daylight is the same as air temperature because you don't bring the direct sunlight. The problem is if you use sunlight or you allow sunlight, which is the direct light, yes, that would bring heat. So my point is, in the tropics, I think you should not have direct sunlight, which means if you don't have direct sunlight, you probably do not really need the light tube or light well, unless you got a building. So light well or light tube would be effective if you have, let's say, 2-story house, and there's no way you can have a window, and you have to bring light from the roof, and so you bring it through light well. Then I think it makes sense. But as long as you can have windows that can be protected from the direct sun, I don't think the heat that comes into that would be hot air. I don't think you're going to bring hot air. It's just the same air temperature outside. That's my answer. So if you really use daylight, so basically if you have a, if you want to put skylight, for example, don't put the glass facing the sky. You need to, is that somebody doing something so I can draw? Or are you trying to draw something? Let me just see where is, how come I don't see the annotate? Oh, maybe I should put some screen, eh? Let me just, so I just want to do, let me just do, where is the annotate? How come I can't find my annotate screen? I'm just gonna stop. Can you find an annotate? Where is the annotate? I can't see annotate. I'm sorry, I was trying to draw, but I cannot see the annotate button on your screen. So let me just add something else here. Okay, so not this one, hang on. Let me just go to, okay, so let me share a screen. So what I'm trying to say is, if you have, if you want to draw, if you want to, can I draw? Let me just see, why is it not? Okay, so what I'm trying to say is, if you have a building, let's say if this is your building, sorry, I'm just using, all right. So if you want to put skylight, for example, my suggestion is in the tropic, never put skylight that's facing like that, because what happen is you just bring in direct sun here. So I think the way you do it in the tropics is, I suppose you put a window there, and there should be probably a roof, or maybe with the shading like this, whatever it is. But let's say just the roof. So then your, oh, sorry. I'm just gonna use this quickly. All right, there you go. So then what happened is you got sun coming here, but hopefully that would be blocked by this skylight, maybe like that. All right, so the skylight now is vertical, you don't get direct sun, then you got daylight rather than sunlight. Whereas if you get it like this, there's sunlight. But again, as I said, if you have a building, say a ground floor, and there is no way you can have window here, then maybe, yes, you can put a sort of light tube here. That probably would work. But as long as you can have windows, I would suggest you use window. Okay. All right, any other question?
Okay. Is that clear, Tika? The answer? Prof. Ira, I just want to continue from Tika's questions. What if the condition, this light tube or light well, is being applied in, how to say, in a very dense populated houses. So they don't even have like vertical wall. They just side by side with other houses.
Sure. I think in that case, if that's the only way you can get light to the room, I think, you probably just have to do that. Or maybe, I mean, there's of course several ways of of doing it. You could have have, I don't know, if it's two-story, you're talking about two-story building or just even one-story building?
Yeah, even one-story building, because
even one-story
like
building. I think if you're in a dense situation, it's very hard. And look, I have to say also in terms of cooling the building, once you got to the very dense dense setting, having natural ventilation would be pretty hard. Probably what you could do is using earth cooling principle. So you put in sort of cool tube under the building, and then so you extract air from above the building. So you got a tube going down and then go under the building. So the ground under the building would help cool the house, or cool the air, sorry, and then you extract that cool air up again. There's an example on that using ground cooling. I don't know if it has been applied in say areas like Jakarta. I went to, anybody went to the Green School in Bali? Have you been there? There is a bamboo green. Have you been to Green School? Tria, you did? Yeah. So I don't know if you remember, there is a room, what they call it, a refuge room. So it's a classroom. When it gets too hot, they said they bring all the kids there and they close it, this plastic kind of, it's like a plastic bubble. And then what they do is they open this fan on the lower cupboard. It basically bring cool air from the ground. So they have pipes under the ground. So that's worth trying, having the cool pipe principle, bringing cool coming from the ground. But in terms of getting light, I think when you don't have much on the side, all you can do is coming from the top. But still, my suggestion is make sure that you don't bring in direct sun. I think the nice thing about cool tube though, because although it's it's a circle like this, the heat in a way doesn't go straight to the room, because it just bounces back and forth inside the tube, so you don't get the direct sun. Yeah, so that is a possibility.
Okay.
It is tricky when it comes to, and that's why I think the challenge, I guess, in a place like Indonesia, particularly if you're in a dense location, if there's not much space for openings and it's very dense, and then you feel so hot, there's no air movement, then of course air conditioning becomes the solution, because it's so much easier to control the air inside the building. But the problem is, once you put air conditioning, of course, the heat from the air conditioning will just get out again. So you just keep adding heat to the surrounding environment, and you keep using the air conditioning. So it's just like a vicious circles. Despite the fact there should be other way that you can do it. And again, you can try to simulate it. All right, there's another question. Thermal comfort in high-rise buildings, the current yes. Droplets can easily spread in the room. Yeah, it's correct. Even if some airport recognition is turned off to prevent spread. That is totally right. And I think we do need more research on this. And we are actually thinking of, planning to do some research on this. I believe some of the problems, particularly in Australia, we got a lot of cases in nursing home and aged care facilities, fully air conditioned. It's so easy for it to the virus to be transmitted, because it is airborne as well as through droplets. So having fresh air is so important. And unfortunately, when you have air conditioning, you tend to close the window. And that means the air just going around, and you just infect everybody. So in multi-story buildings, even before COVID, there have been some multi-story buildings not just in Australia, anywhere in the world, that try to increase or having 100% fresh air. So even though it is air conditioned, the air that is brought into the air conditioning actually is 100% fresh air. So it draws fresh air to the building through the air conditioning system, and then 100% will be extracted out again. So it keeps getting fresh air into the building. The problem with using 100% fresh air is it's expensive, because imagine if it's, so does everybody learn about air conditioning already? How air conditioning works? Is there any class in air conditioning in architectural week? Yes? No? I just want to explain a little bit, because with air conditioning, basically what you do is you remove the heat from the building, replacing it with a mix of, usually it's a mix of outside air and return air. So if you use 100% outside air, let's just assume outside is 30 degrees and inside is, we want to make it 25 degrees. So you have to cool that 30 degrees temperature to 25 degrees. So you have to have the condenser to condense the air. And so it is a lot of energy to do that. Now, usually to minimize the energy, you use return air, which means is the air that is inside the building, you extract maybe about 40% of that, because the temperature of the air inside a building could be about 27 degrees. So you want to achieve 25, but after people, use the building, or in the room, people generate heat, breathe out air, and so on, the temperature would increase, set to 27 degrees. And then you mix it with the 30 degrees outside, you don't have to, so 27 plus 30, if you mix it, it becomes, say, 28.5 degrees. So then between 28.5 to 25, it's only 3-degree difference. Whereas if you use 100% fresh air, you probably have to cool the air as much as 5-degree difference. So using return air is cheaper. And that's why a lot of buildings are doing this. I mean, even your air conditioning at home, what it does is, once you turn it on, it just keeps cooling the air inside the building. So you can imagine, you don't even take the air out. It's just the air inside your room getting extracted back to the air conditioning, and it just keeps circulating it back. So you never get fresh air in the split system of the air conditioning that we use at home. In a public building, we got fresh air, but we also have return air, and you mix it. And that's the reason why you can get sick in the commercial building, because you use the air that is being breathed out by somebody else. So if somebody gets sick, they release their breath, the air get extracted back to the air conditioning system, and it get used again. That's why you get sick. So the key in the multi-story building, I think nowadays, we really need to think about using 100% fresh air and find a better way so it's not too expensive. Or let people open the windows. I mean, that's the challenge, of course. Most commercial buildings, high-rise buildings, will not allow people to open the windows for safety reason. People can jump. But there should be a way, maybe we should think about having top windows that can be open. So at least if you need some fresh air, you can have some part of the windows that are openable without without risking people's life. People are not going to jump because it's high up, things like that. So I think it does really make us rethink the way we design the building, this COVID issue, because in a closed room it's just bad, but we just get used to it. And I think we need to change the way we design, don't you think? It is a problem. It is a big issue. And imagine movie theater. Wow, that's just a breeding ground for virus, because you're just inside the room for 2 hours, and depending on the system, they probably will have some air taken out, but most of it is just return it back to the space. So they go through filter, of course. When you take the air out, it goes to the filter, but some part of the air would still go back. So yeah, it is what we call the sick building syndrome. You probably know that when you have a closed room, you just get air being contaminated all the time and just make other people sick. Yeah.
Okay. Thank you so much, Prof. Ira. Do we still have questions from the audience? No? Okay, I think it's quite tough, the discussions, Prof. Ira, and it's very important. Okay.
Very good questions. Let me just see. I just make sure that I don't miss the questions. Let me see.
Okay, sure.
Okay, that's fine. Okay, good.
Okay. Okay then, Prof. Ira.
All right.
Before we close the sessions, maybe I would like to read some kind of conclusions from this lecture. The first one is about the case that you mentioned about building thermal. It's becoming a community now, right? Just like a few centuries maybe. And also the human is the real actor, and it's local, it's never be universal, right? Okay, the second one is about when you're mentioning about IES, design builders, and also we have Autodesk, for example. It's very sensitive case because it depends on the one the engine who's working it. This is just a tool. I also experience myself with my students also in our research. We need to check and recheck about the data that we put in. Otherwise, we get lost and questioning why it's like this. Yeah, it's so different with reality. Okay, and
sorry,
then,
Ova, if I could interrupt there.
Yes.
It's really important to never say that that's what the tool gives me. You know, that's what Design Builder or Revit or whatever simulation gives me. You have
don't
to
don't blame the tools.
don't just take it as the truth. If it doesn't make sense, you need to make sense of the answer, or if it doesn't make sense, then find out why. But yeah, don't use the tool as an excuse to say, yeah, that's the answer I get. Well, might be a wrong answer. So yeah,
yes, I think it's quite sensitive because you know, you mentioning about the one who fill in the questionnaire within the long hour or night hour, the restless people. I can imagine if this was done by this kind of people, yeah, during the very case sensitive. Anyway,
that's true. That's true. Yeah.
Yeah, okay. And last point, Prof. Ira, I would just want to recall our previous topic about the social dimensions of architecture in sustainability. I think today we also emphasize the very important role of human. Either they are the occupants, they are the users, they are the engineers, the planners, and so on and so forth. They are really the core of all of activities that we have done, right?
That's very true.
Okay, I think that's all the summary from my side. Maybe you would like to say something, Prof. Ira, before we close this lecture for today?
No, that's good. I mean, maybe another time. I would just like to see, or maybe another time, what is being taught, what activities that now. I think there's a lot of things that have changed so much since I left OE. When was that? Back in the 90s.
Which year then?
I think, yeah, the last time I was teaching there was 1990. So, yeah. Oh, no, and then I came back for a few months in 97. Yeah, it seems to me you've done so many amazing, great things, exciting things there. So, well done. But we'd like to see more. So maybe one day you can take me around doing a virtual tour.
Of course. You're almost welcome, always.
That's right. That's right.
Okay, then, Prof. Ira, I think now it's about the time. Yeah, we will meet again on 15 next week. Yeah, but maybe not in this hour, but we started from 1 o'clock. Yeah, we will talk about building energy simulations in class of bangunan hemat energi or building energy efficient.
Sure. So what do you expect me to talk about there?
Yeah, actually the class is again another class of our graduate or undergraduate. Yeah, we learn about any aspect like the energy, the water conservations, also the lighting things. But we mostly use the Edge software. We have here Kak Laksi also the lecturer. So
Edge software, never heard that.
Edge software is an open software. Also, is derived from the World Bank, the IFC. Yeah, I think it's quite new also, Prof. Ira.
Okay, and what do you expect me to talk about? Because if you already learn it, if the students learn it already, what do you want me to? Is it giving examples? Is it about how to? Is it about yeah? Is it or is it about do you talk about embodied energy as well?
Yes, we are. Yes, we are.
You do.
But
okay.
I think you can also share your experience in terms of building simulations. That's what we have now, but specifically into an energy because we will talk about building energy simulation.
Okay.
In the class.
Sure. Okay.
Yeah. And I think it's also very important that what you did just now, you try to put us in the same level before you're getting into your core. I think it's very brilliant.
Okay, good.
Yeah?
Good. All right.
Okay, then. Yeah, thank you so much again, Prof. Ira.
Thank you.
Yeah.
We'll see you next week.
Yes, see you next week. Bye-bye. Stay healthy. Bye. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang semuanya. Terima kasih banyak.
Terima kasih Bu Ova, Prof. Ira.
Thank you, Prof.
Thank you.
Thank you. Terima kasih.
Terima kasih sama-sama. Bye.